getting set up. So the next talk is called Timed Concurrent Language for Argumentation, an Interleaving Approach. And the presenter is Carlo Taticchi.
Yep, so thank you. Can you see my screen?
Yes.
Should I start?
Please go ahead. Yeah.
Yeah, thank you. So good morning or good evening, everybody. The work I'm going to present is about timed concurrent language, which uses argumentation. And in particular, in this implementation, we use an interleaving approach. Before even starting, let me spend a few words about argumentation theory. So it is a discipline in the AI, and it basically deals with information and with conflicting information. So we are interested in the kind of relations between facts, for instance. And you can think about two counterparts. It's easy to think about positions who are debating, for instance, upon some kind of argument. And they both have two main goals. One is to convince the audience about their point of view. And the other one, they also want to defeat the opponent. So whatever the opponent is saying, they want to defeat their point of view, their topics. And at a certain point, they might even try to convince the opponent themselves. So argumentation is about putting these facts together, understanding the relation between them, and trying to figure out which arguments are the best, which one could win an argument, debate, for instance. And since we use this example of a dialogue, of a debate, you can imagine that these arguments evolve through time. So they are not still the same. They are not all available at the beginning. They are added meanwhile the discussion goes on. And so we wanted to provide a language for enabling intelligent agents to reason in such a way to mimic the natural human way of thinking. Okay, this is an overview of what I'm going to present today. A brief background on argumentation frameworks, which are the building blocks of argumentation theory. Then I'll show you the syntax and the operational semantics of our language. And I'll also show you a small example on how to use constructs for our language to model debate. Okay, so an argumentation framework is a directed graph. You can see a tiny example here on the right. And the nodes on this graph are the arguments. And the edges between them are called attack relations. So in this example, we have three arguments. And the first one here at the bottom might stand for, I want to go to the park. And then you can see that there is another argument, which is attacking the first one. This other argument could mean, wait, you cannot go outside. It's raining, you will get wet. And then this third argument with an umbrella means that you can just go outside, even if there's bad weather, if you bring an umbrella with you. So there is this sort of reasoning going through these three simple arguments, but we are not really interested in the arguments themselves, so the meaning of the single argument, but instead we are interested in abstracting the arguments and just looking at the structure of the underlying graph. So let's use this slightly more complex example for these basic notions of argumentation. And I'm going to introduce the so-called semantics. So the goal with this framework is to look for a subset of good arguments. And they are good because they share some nice properties like conflict freeness, which is you don't want to select arguments that attack each other. It would be like if in a debate, I contradict myself. I just want to avoid it. So I look for conflict-free subset of arguments. And argumentation semantics are criteria which I can use to choose the right arguments to use, for example, in a public speech. Here you can see three of these semantics: the conflict-free, the admissible, the complete. Each one of them has strict requirements for the arguments to select. There are several more in the literature. we just need to know that you can use them to look for a nice argument to choose for your debate. And the notion we are using for this work is that of credulous and skeptical acceptance, meaning that you can find more than one subset of arguments which satisfy these conditions. For example, here you can see that there are three a complete subset of arguments. And we say that an argument is credulously accepted if it belongs to at least one of the subset I can find. And I can say that an argument is skeptically accepted if it belongs to each of the found subset. Okay, so this kind of semantics allows you to look for subset of arguments. I can use a different approach, which leads to the same result, which is labeling-based semantics. So instead of having criteria for selecting subset of arguments, I have rules which allows me to label the argument by using, in this case, 3 labels, and in arguments, out, and undec, which stand for undecided. And here, the meaning is that the in arguments are those which are accepted. And in that, indeed, there is a connection between labeling-based semantics and the classical semantics that we saw in the previous slide. So we decided to use this approach with labeling semantics, and I'll show you in a few slides how we implemented those kind of semantics to enable reasoning for our intelligent agents. Now, coming to our language, I say that we wanted to provide a language to allow intelligent agents to interact, and in particular, we wanted them to be able to reason on the information they possess through notions coming from argumentation theory, for instance, the semantics we've seen before. And we enable this by using an argumentation framework structure for the shared memory between the agents of our system. So since the knowledge base, the shared memory of the agents is an argumentation framework, they can use argumentation semantics to look, for instance, for facts that are accepted by the other agents, or facts that cannot be accepted, for instance. Of course, they also we also can implement more complex interactions starting from this one. And this is a concurrent language, so of course operations can occur in parallel. And in particular, we use an interleaving approach, meaning that we can execute basically just one operation at a time. Like in real life situations where processor can only handle a few processes at a time. And here I reported the syntax of our language. We'll see this in the next slides in detail. For now, I just want to say that we have a set of actions that each agent can perform, and some of the actions can be an expression. And the interesting part is that expressions in our language have timeouts. And in particular, you only have a limited amount of time to execute an expression. When the timeout expires, the expression will automatically fail once it is executed. So we are using an interleaving approach. This is opposite to the maximal parallelism approach, in which instead an infinite number of processes can occur at the same time. This is, of course, this cannot happen in real situations. So we found the interleaving approach more fitting to the real cases in which we might implement this language. And in our system, each action takes exactly 1 unit of time to be performed. And I say that expressions have timeouts, which we want to decrease at each computational step in order to keep track of what happened in each parallel branch. But now we have a problem because I said that we only execute 1 operation at a time, but in the meanwhile, we want that all the timeouts on the expression are decreased at each step. And so we just use 2 kinds of operations. we use two labels for actions. We have omega actions and tau actions. The omega actions are the real computation steps, so the actions which have to be executed by the processor. So those which access the shared memory, that manipulate the information in the knowledge base. While tau actions are just used for time elapsing. So we use a time action every time we need to just decrease the timeouts on the expressions. And for this tau action, we can use maximal parallelism. So we can have how many tau actions we want in parallel branches and just one omega action. Okay, let me show some of the operation that we implement in our language. I'll start with the addition and removal of information, which is what you might expect. You can add and remove facts from the knowledge base. In our case, we are talking about arguments and attacks between them in the shared memory, which is an argumentation framework. Then we have a syntactic check. We can ask the system, is argument A in the shared memory, for instance? And you can see that we have 4 different cases. So in the best scenario, the condition is satisfied. That is, the argument you're looking for is actually in the knowledge base, and the timeout is not expired yet. So you perform an omega action. This is a real computation. You require the processor to take care about this operation. And you just proceed with the consequent step. So the check succeeds, you can go on with the computation. It might also happen that the condition is not satisfied. But if the timeout is still greater than 0, it's not expired yet, and the processor is taking care of the operation, so you are performing an omega action, you decrease the timeout with this t-1 here, and then you continue with the execution of the program. In this case, the check operation will be repeated in the consequent step. It might happen that the processor is busy because it is executing another branch, another parallel branch. In this case, when we need to decrease the timeout in this check operation, we just use this rule here, which has a tau actions, and so it's executed with maximal parallelism. And we don't even need to check the premises of the rule, because we don't, it doesn't matter. We don't care about whether this check is satisfied or not. We just want the timeout to decrease if it is still greater than 0. When it expired, like in this last rule here, the operation will fail as soon as the processor executed it. Okay, this check was syntactic. That is, you just look at the shared memory. If the argument you're looking for is there, then the check is satisfied. We also have semantic tests. In this case, we ask, is argument A acceptable with respect to some semantics in the shared memory? And so here the argumentation part is used in the language. And we have a credulous test as well as a skeptical test according to which kind of acceptability we want to test for our argument. And this reflects the same occurrence as the syntactic check. So you have the same 4 cases according whether the operation is being executed by the processor, or is it just a timeout that is being decreased, or even if the operation failed because the timeout expired. Then we have hidden variables and procedure call. I will talk about this later on because we have some future work involved in them. Okay, we are talking about a concurrent language, so of course we have rules for parallelism. We want still operation to be executed in parallel branches. And the parallelism is the classical one, that is 2 actions executed in parallel succeeds if both the agents succeeds, and if just one of the parallel branches fail, all parallel agents fail. And then we have a guarded parallelism, in which instead all the expressions that can be executed are executed, and in order to the whole guarded parallelism construct to fail, we need all the involved agents in parallel branches to fail. Okay, then we have non-determinism, which again is the classical one, and we choose either of two possible expression, and we execute one. We just don't know which one will be executed. We can say random, chosen by the processor. And then we have a sort of prioritized non-determinism, which realizes an if-then-else construct. So we first try to execute the leftmost expression, and if it succeeds, we just go on with computation. And if the leftmost expression fails, like in a classical if-then-else construct, we try and execute the other branch. And of course, this other branch can either succeed or fail again. Okay, these were some of the operations which are allowed by our language. And I'll just show you an example of how we can model a dialogue, just to show you what we can do with this language. So let's imagine that we have three people which are discussing about oyster farming. So we have this fancy example with oyster, and so here you can see a conversation, let's say, between these three people. And for instance, Alice is saying, you should really use fertilizer. It increments the amount of oysters you get. And Bob is a little concerned about lake pollutions, and also Carol is against the fertilizer. And again, we don't really care about the meaning of each sentence, each argument. We just care about how these arguments can be put together. So we can see that this conversation here can be represented through this argumentation framework, in which each arguments correspond to one of these sentences. Okay, now, of course, the conversation do not happen one shot. The arguments come one by one in the shared memory. And so this is an example of how we can implement such a dialogue by using constructs from our language. Of course, there are many possible ways. This is just one. We can imagine that the conversation starts with argument A being added into the shared memory. So the argument A is the only one in the memory at the beginning of this conversation. And now, since A is in the memory, these three checks in the parallel branches can be satisfied. So it's sort of we enable these parallel branches. And now the processor can choose and execute one of those. And in this case, we choose, or we or the processor, we choose to execute this branch here. So we perform the check operation. The argument A is in the shared memory. So this is satisfied, and we can proceed with the consequent operation, which in this case is an add operation. So we add an argument B together with its stack from B to A. And okay, now we added the argument B to the shared memory. So we enable another check operation, meaning that if this check is executed, it will be satisfied. And for instance, is this check here, in which we look for argument C, is executed now, it will fail. Its timeout will be decreased, and the operation need to be performed again in a later step. And okay, we continue. We perform the check operations, and whenever we found the argument we're looking for, we can proceed by adding the argument specified in each branch. Here we added argument D and C, and then since C and D have been added now, also E can be added. But for this step, the processor decided to add the argument G, which is stuck in B. Then we add argument E, which is stuck in C and D, and eventually we also execute the last parallel branch by adding the argument F. And you can see that the framework we obtain is the same that we represented before from the real conversation we saw on screen. And we obtain this through operations written in our language. And to ease the use of the language, we are also implementing a web interface, which you can basically write a program, and then you can run the program and obtain the output. And in the meanwhile, you can see the status of the shared memory. So we can see at each step which are the argument and the attacks being inserted or retracted from the shared memory. And you also have sort of availability functions for the arguments. In this example here, for example, you can see that argument B is being added at step 3, and at step 6, the same argument B is removed. So argument B in the conversation, debate, whatever the program is representing, B is available from t equal to 3 until t equal to 6. Okay, to conclude, we presented this concurrent language that enables intelligent agents to reason through argumentation notions. And I showed you the syntax and the operational semantics of our language. I pointed out that we used an interleaving approach. And we can also model debates, as we saw from the example of a few slides before. We are also working on web implementation of the language. For the future, so I mentioned that we have existential quantifiers, and we would like to use them for modeling a local store for agents. So you might think about this existential quantifier as a way to give a local store for agents, so that each agent can bring some information private. So it's easy to think that some of the agents in some situation do not want to share all their knowledge with the rest of the agents in the system. And maybe they want to elaborate a winning strategy by using some of the knowledge that they own, but the other arguments does not. So we want to model also this kind of interactions with local storage, and we want to use existential quantifier for it. Then we would like to use the basic construct that I showed you to model more complex interaction. For instance, those of negotiation and persuasion, which require a sort of a guided interaction between the involved agents. Since we are using argumentation to enable reasoning for the agents, we would like to devise notions of acceptability that are depending on time. For instance, now we are able to ask, is argument D accepted in the shared memory? And this would mean, will I win the debate if I bring forward argument D? But we also would like to implement something like asking whether an argument D is acceptable in a given interval of time. So something like, is argument D acceptable from time t1 to time t5? This would allow to devise a time-based strategy, for instance, for even more complex interactions. And finally, since we are basically manipulating the beliefs in a knowledge base, we would like to carefully study the connection that we have with the belief revision theory, with the AGM framework. And okay, so this concludes my talk. And if you have any questions, I'd be glad to answer.
Yeah, thank you. Let's thank the speaker however we can. So we're running a bit behind now, and I've not kept people to time, so we should probably have at most one quick question if there is one, and if not, I'll ask a quick question, but I'll give people a minute to think. Okay, so I'll ask my quick question. So have you thought at all about so you have your argumentation language and you evaluate things and you get an answer or the end result. If somebody is curious about how the end result was arrived at, is that something that's provided in the form of some kind of explanation built into the system, or is that something that you would consider adding in the future?
Thanks. So the question is if we somehow explain the results of the system. So an argument is accepted, but why? Is that the questions?
Yeah.
Yeah. Okay. So argumentation naturally implements a sort of explanation. Indeed, we have that we can follow a justification process for an argument to be accepted. I talk quickly about these argumentation semantics, but you basically have criteria which tells you argument, say D, can be accepted because there exists another argument that is justifying its status. So the semantics automatically provide you with an explanation. So you can build a justification for the acceptance of an argument. So that is intrinsic in the model. Of course, we could make it explicit with some more complex system, but yeah.
Okay, thank you.
Answer the question.
So in the interest of time, I think we need to move on, but thanks for